Here we're going to do something very practical. Get everyone to the same baseline in Java before we start concurrency in earnest. Some of you already code comfortably in Java, others might be coming from Python, C or C++, or maybe you've only seen a bit of Java before. This primer exists so that threading and synchronization won't feel like a second language on top of the language. As we go, keep this mental promise. We are not learning Java for Java's sake. We're learning the pieces that will matter when we run multiple threads, share memory, debug race conditions, and reason about execution. Java's runtime model, bytecode, JVM, JIT, or JIT, garbage collection will show up constantly once we start concurrency. Java is both a programming language and a platform, and that's a key distinction. As a language, it's high level. You write code that's readable and structured, not raw machine instructions. It's object-oriented, meaning we organize code around objects and classes, which is not just style. It affects how state and shared data are structured, and that becomes important in concurrent programs. Java is also statically typed, so the compiler checks types early. That's one of the reasons Java tends to fail earlier than Python when you do something inconsistent, often before you even run the program. Now, the most important conceptual point on this slide is Java is compiled and interpreted, which sounds contradictory until you understand the pipeline. You write myprogram.gaa, then you compile it with javac into myprogram.class. That .class file is not native machine code, it's bytecode, a portable intermediate form. Then you run java myprogram, which starts the JVM, loads the bytecode, and the JVM translates it to actual machine instructions. So why do this two-step approach? First, portability, write once, run anywhere. The same bytecode can run on Windows, Linux, Mac OS as long as there's a JVM. Second, security, the JVM can sandbox and restrict what code can do. Third, performance, the JVM uses a JIT compiler to optimize while running based on what the program actually does. And finally, memory management Java gives you garbage collection, which reduces entire categories of memory bugs. That convenience matters even more once your program is multi-threaded, because manual memory management plus concurrency can become a nightmare. Let's make the ecosystem feel concrete. The flow on the left is the whole story. Source code.yay goes into javac, producing bytecode.class. Then the Java command runs the JVM, which executes that bytecode and produces native machine code internally, which ultimately becomes program execution. This is why Java is called a platform. The JVM is the platform layer, and your code targets the JVM. Now, a quick comparison so you can anchor your expectations. Compared to C/C++, Java is usually easier and safer. No pointer arithmetic, no explicit malloc free, and the runtime checks more things. The trade-off is typically overhead and sometimes lower peak performance, though the GIT can be surprisingly fast in long-running programs. Compared to Python, Java is faster in most cases, but also more verbose because static typing and class structure require more explicit code. Compared to JavaScript, the emphasis is different. Java is strongly typed and traditionally used heavily in back-end systems. JavaScript has a different runtime and type model and is ubiquitous in browsers. Finally, you need the three key acronyms straight, because students mix them up all the time. JDK is for developers. It includes JAVAC and tooling like debuggers. JRE is the runtime environment, JVM plus core libraries, traditionally what you need to run Java. And JVM is the virtual machine itself, the engine that runs bytecode. The JVM is platform specific. There's a different JVM build for each OS/architecture, but your bytecode remains the same. That separation is exactly what enables run anywhere. Here's the canonical first program, a class called Hello World, with a main method, printing a line. But we're not doing this as ritual. We're doing it because every part of this structure teaches you how Java expects programs to be shaped. Start with public class Hello World. Class is the basic unit of organization. Public means it can be accessed from anywhere, important, once you have multiple files or packages. And the name matters because Java is strict about naming conventions and lookup rules. This class name is also your entry point label. It's what you'll run. Now the centerpiece is public static void main string args. Java begins execution at this exact method signature. Public means the JVM can call it. Static means it belongs to the class, not to an instance, so the JVM can invoke it without constructing an object first. Void means it returns nothing. And string with open and closed brackets, args, is simply the array of command line arguments. Later, when we launch concurrent programs with arguments like number of threads, problem size, or mode flags, that args is how we configure behavior without touching the code. Finally, system.out.println is your first interaction with standard output. System is a built-in class, out is an output stream. Plinlun prints and adds a new line. It looks simple now, but as soon as multiple threads print at once, you'll start noticing interleavings, partial output, and ordering effects. So even hello world is a seed for concurrency intuition. This slide is basically a checklist for avoiding frustrating errors. First, pylomeme must match the public class name exactly and case sensitively. HelloWorld.ja must contain public class hello world. If you name the file hello world.ja, many systems will treat that as a different name and Java will not forgive you. This is one of those Java is strict moments. Second, one public class per file. You can define additional helper classes in the same file, but only one can be public, and the file name must match that public class. This rule shapes how Java projects are organized as they grow. Third, the main method signature must be exact. If you misspell it, change the parameter type, or remove static, the JVM doesn't guess. It simply can't find the entry point, and you get a runtime launch error. Then semicolons. Most statements end with minus assignments, method calls, returns, but class and method headers do not. And finally, curly braces define blocks and scope. Missing a brace can produce error messages that seem totally unrelated to the actual mistake, because the parser gets confused far from the missing brace. The beginner mistakes list is basically reality. Mismatched file name, missing semicolons, wrong main, missing braces, and keyword typos like public instead of public. Java keywords are case sensitive. The upside is once you internalize these rules, Java becomes very predictable, especially helpful when debugging concurrent code where predictability is your friend. Let's run this like you would in real life. Step 1. Create helloworld.ya with the class definition in the main. Step 2. Compile using javac hello.world.ja. At compile time, Java does 3 big checks: syntax, types, and then it generates the bytecode file helloworld.class. The key point, if compilation fails, there is no .class file produced, so you cannot half-run a program that didn't compile. Then step 3, run with Java hello world. Notice the rule, you run the class name, not the file name, and you omit the class extension. That's because the JVM is looking up a class in its class path, not executing a file the way you might in C with byte./.out or Python with pythonscript.py. Also note the same directory or class path line. This matters a lot later. As soon as you have multi-file projects, packages, or build tools, you'll be dealing with class paths. And when we run concurrency demos, like launching a thread-heavy benchmark, you want the execution environment to be boring and correct. So your debugging focuses on concurrency, not on why can't Java find my class. This is where Java becomes visibly different from many languages. The class file contains bytecode instructions for the JVM. If you run javep-c hello world %clax, you see a low-level instruction listing, loads, invokes, returns. You're not expected to write bytecode, but you should know it exists. Because it explains the execution model, Java source becomes a portable intermediate representation, and the JVM is responsible for executing it. Now, error categories: compile time versus runtime. Compile time errors are what Java C catches. Syntax errors, type mismatches, missing semicolons, things the compiler can decide without running the program. Runtime errors happen while executing: division by zero, null pointers, array bounds issues. The important concurrency takeaway is that some of the nastiest bugs, race conditions, deadlocks, visibility issues, are often runtime phenomena. Your code compiles just fine, and then fails only under certain schedules, loads, or machine timing. So the takeaway block is exactly right. Javac catches many mistakes early, but not all. In concurrency, you'll learn to love the compiler for what it prevents, and also respect the runtime for the surprises it can still deliver. Here we're seeing the standard Java unit, one file containing one public class, and the field main matches the class name. In circle.ga, the public class is circle, and that's not cosmetic. Java's compiler and runtime both rely on this convention. The example also shows the 3 ingredients of a basic class: state, double radius, construction, a constructor circle $R that initializes the state and behavior, a method area that computes something using that state. Even before concurrency, this is the foundation of how Java organizes code. Notice also that main is placed inside the same class. That's not required. Main can live in a separate driver class, but it's convenient for small demos. Inside main, we create an object new circle 5.0, then call cEra and print the result. That already hints at Java's object model. Methods are typically invoked on objects, and objects carry mutable state. Later, concurrency will basically be about what happens when multiple threads interact with that state. The right column is the practical workflow, javacircle.ja. Then Java circle. You compile the file, but you run the class. And the output is a floating point number. Minus don't get distracted by the specific digits. The point is that your program executed and printed a computed value. The rule block is the thing students forget most. If it's public, the file must match. Break that rule and Java won't negotiate. Now we keep a single file, but place multiple classes inside it. The key constraint is still there, only one public class, and that public class name must match the file name. So the file is main.j, and it contains public class main. Then we add class helper below it, but it's not public, which is why this is legal. What's important here is that Java's compilation step will generate multiple class files from one.ja file. When you compile main.ja, the compiler produces main.class. That is a very concrete way to understand that a file and a class are not the same thing. A source file can contain several class definitions, and each class becomes its own compiled artifact. At runtime, you still run Java main. Because main contains the main entry point, main creates a helper object and calls do work. This is also an early taste of modularity. One class drives the program, another class encapsulates some behavior. In concurrency, you'll later see classes used this way to isolate thread logic, shared resources, or worker tasks, so getting comfortable with driver and helper classes now pays off later. This slide transitions to how real projects are structured. Multiple files, each holding a public class. We split student into student.yay and the test driver into teststudent.yay. That is the most common pattern in Java. One public class per file, and your executable class, whatever has main, just uses the other classes. Notice a subtle but important convenience. You can compile both files explicitly, javacstudent.ja teststudent.ja, or compile only teststudent.ja, and the compiler will find student automatically because it's referenced. This is Java's compilation dependency resolution at a small scale. It feels friendly now. Later, when packages and class paths enter, you'll want a clear mental model of where Java is searching for reference classes. The key points list is basically the rulebook you should internalize. Public classes need their own file. File names must match. Non-public classes can share a file. The compiler resolves references, and a single .ja can produce multiple .class files. For concurrency, the big takeaway is the unit that gets executed is a class, bytecode, not a file, and managing many classes cleanly is what keeps concurrent code from turning into spaghetti. Packages are Java's way of scaling from a few files to a real codebase. The motivation list is exactly what you feel in larger systems. Packages organize related classes, avoid name conflicts. You can have multiple student classes in different packages. Control visibility, access rules depend on package boundaries, and they mirror directory structure so your file system matches your namespace. The most important rule here is the one students break constantly. The package name must match the directory structure. If your file says package.com university, then it must live under ./.com university relative to the source root. That's why the directory tree shows project slash iss student.yay. Java is strict here because it uses package names as part of how it locates compiled classes. In the example, student.ja begins with package.university and then defines public class student. Pay attention to the order. Package line first, then imports, if any, then the class. The class also includes a private field and a method display. This is a small but important bridge to concurrency. Encapsulation matters. If you make state private and expose controlled methods, you have a fighting chance to later add synchronization or thread-safe patterns without breaking the rest of the program. Once classes are in the same package, using them becomes straightforward. In main.ja, we declare package.com university, and then we can directly refer to student without any import. The reason is simple. Same package means same namespace by Java knows where to find siblings. The what to remember bullets are exactly the habits to build. Files in the same package see each other directly. The package name must be at the top, and public classes can be used from other packages with imports. This is the point where visibility starts to mean something beyond public/private. Java has access levels like package private that are extremely useful when you want to hide implementation details inside a package. And the common mistake is painfully real, forgetting the package line. If you do that, the class falls into the default package, which behaves awkwardly and doesn't play nicely with proper packaged code. In practice, avoid the default package except for the smallest throwaway examples. If you plan to build anything larger, especially concurrency labs, use packages early. Here we connect the language level idea of packages to the runtime level idea of class path. In application.yay, which lives in package.com set ep, we want to use student from .university. The clean way is importing the specific class, import.u.university.student. Java also lets you import everything with import.university, but you should use that sparingly because it can hide name collisions and make code harder to read. And there's always the fully qualified option, write.university, student explicitly verbose, but it removes ambiguity. Now the compiling and running commands are the practical payoff. Java c-d bin means compile and place the .class output under bin following the package directory structure. Then when running, you must specify the class path, java-cpbin.com app and negation. Two details matter. The JVM needs to know where the compiled classes live, -cpbin, and you run using the fully qualified class name that includes the package .com.application, not just application. So the mental model block is gold. Package is your namespace, while class path is the JVM search path for bytecode. And this will become non-negotiable for concurrency labs. If your class path is wrong, nothing runs. If your packages are messy, it becomes harder to structure thread code, utilities, and shared components cleanly. Getting this right early saves you hours later. The class path is one of those Java concepts that feels annoying until you realize it's simply answering a basic question. When the JVM sees a class name, where exactly should it look for the bytecode? The class path tells the JVM where to find class files, and it can point to either directories which contain package trees or jar files, which are basically zip-like archives of compiled classes and resources. The mental model on the slide is the one to remember. The class path points to the root of a package tree, not to the package folder itself. If your class is commiapp main, then the JVM expects to find it at com/myiapp/main.class under some root directory, and the root directory is what you put on the class path. That's why .cpbin works. When you have bin/com/myiapp/main.class, you don't write -cpbin/tom/myiapp, you write -cpbin. Practically, you set it with -cp or -class path on the Java command, or you can use the class path environment variable. I strongly recommend using -cp explicitly while learning, because environment variables can mysteriously affect things and make debugging harder. The examples show typical patterns. -cp means current directory, -cp divided by 2 electro classes is a custom root, and you can combine multiple entries. The separator matters on Unix, macOS, it's a colon, on Windows, it's a semicolon. That single character causes more confusion than almost any Java syntax issue. Here's a clean, realistic project layout. src/ for source, bin/ for compiled output, and lib/ for external libraries like Zon. This separation matters because it reinforces the pipeline. Source code isn't what runs -bytecode runs. And once you introduce packages, the compiled structure under bin/ mirrors the package folders. The key idea is Java C --dbin writes .class files into bin/ following package directories. So compiling a swak/.com/myiapp/main.ja produces something like bin.com myiapp main.class. When running, you use -cpbin and then you run by fully qualified class name, e.g.com.myiapp.main. Again, class path points to the root, and the class name specifies the path inside that root, and we add libraries. During compilation, the compiler needs to see external types too. So if your code imports something from Jun, you compile with Java c-cp lib jun 2.8.jar min-dbin. At runtime, the JVM also needs those classes available. So you run with both bin and the jar, java -cpbin lib jun 2.8 jar.com, iapp main. This is the core two-time insight. Your dependencies must be present at compile time and runtime, and those can fail independently. Jar files are Java's standard packaging format. A jar bundles compiled classes and often resources into a single file. Creating one from compiled output is straightforward. Jar cvf myapp.jar.cbin. Basically says take everything under bin and package it. If you want an executable jar, meaning you can run it with Java 9-jar myapp.jar, then the jar needs a main class entry in its manifest. That's what the CVFA form does. It packages the classes and sets the entry point, like com_myapp_main. There are two common ways you run things: java-jar myapp.jar if the jar is executable, or java cp myapp_jar libgcon.jar.com myapp_main if you're using a jar as one item on a bigger class path. Many real projects do the second because they combine multiple jars and directories in concurrency labs. You'll often have your code in bin plus a couple libraries, so learning to read and write these commands is genuinely useful. Now the failure modes. Class not found exception usually means the JVM cannot locate that class name on the runtime class path. No class def found error is subtler. It often means the class existed when you compiled, but something it depends on is missing at runtime, or the class was present earlier and isn't now. Add in the classic separator mismatch, colon versus semicolon, and forgetting the current directory dot minus, and you get the standard class path pane. The debug tip is perfect. If you can't find com_myaa, verify the file exists at bin com_myapp main.class and verify you actually ran with cpbin. If either is wrong, the JVM isn't going to guess. Let's start with two errors that are almost Java initiation rights. First, public class name doesn't match the field name. In the example, the file is test.yaa, but the class is public class myClass. Java is explicit. The compiler rejects this and tells you exactly what to do. Rename the file to myClass.yaa or change the public class name to match the file. The reason isn't arbitrary. Java's class loading conventions assume a mapping between public class names and file organization. Second, the missing semicolon. Java statements generally end with a semicolon, and in the example system.out.println hello is missing it. The compiler complains with sellabone expected, which is often a very direct hint. In more complex cases, a missing semicolon can cause error messages on the next line or even later. So if you see weird parse errors, scan upward for a missing semicolon. These errors are boring, but they matter because in concurrency programming you already have enough complexity from the logic. You want the language mechanics to be automatic. Treat these rules like typing discipline, small habits that prevent wasted debugging time. This slide is important because it's a classic compile time versus runtime mismatch. The code compiles. Javac test.yay succeeds, but running fails because the entry point is incorrect. The mistake is that main is not static. Public void main string args defines an instance method, but the JVM needs a class level entry point so it can start without constructing an object. This is why Java can appear confusing at first. The compiler is checking the language rules, and a non-static main is legal Java. But the JVM has a separate rule. To launch a program, it searches for exactly public static void main string args. If it doesn't find it, it can't start your program. So Java test throws a runtime error. The fix is simply to use the exact signature. And the exam tip is real. You can write perfectly compilable code that still won't run in concurrency contexts. This kind of distinction becomes even more important because many concurrency failures are runtime phenomena that the compiler cannot rule out. Cannot find symbol is one of the most common Java compiler messages, and it's basically the compiler saying, you referenced a name I don't know how to resolve in this context. In the example, message is printed but never declared. The compiler tells you the symbol is the variable message and points to its location and context. This error can come from a bunch of causes, and the slide lists the real ones. Typos, forgetting to declare something, missing imports or wrong package names, or scope issues, like declaring a variable inside a block and trying to use it outside. A big part of becoming fluent in Java is learning to interpret this error as a name resolution problem. Where is this supposed to be defined? And is it visible here? The fix example shows the simplest repair. Declare string messages equals hello before using it. Later, when we introduce packages and class paths, cannot find symbol can also be caused by missing imports or incorrectly structured projects. So it's worth training students to ask, is the name wrong? Is the declaration missing? Is the import missing? Or is the variable out of scope? Two more classics. First, incompatible types. Java is statically typed, so int x equals hello. Fails immediately, minus string cannot be converted to int. This is Java doing you a favor. It forces you to be explicit about what you mean. If you want a number from a string, you parse it. For example, integer.parseInt12.3. This becomes critical later when concurrency code manipulates shared state. Strong typing helps prevent accidental misuse of data across threads. Second, missing closing brace. In the example, the main method is closed, but the class itself is not. The compiler reaches the end of the file, still expecting a closed bracket, and reports reached end of file while parsing. This error often happens when you're editing quickly and lose track of scopes. The fix is just adding the missing closed bracket, but the deeper habit is always keep your indentation and braces consistent. In concurrent code, nested blocks are common, synchronized sections, try finally blocks, loops, and brace. Discipline prevents both syntax errors and logical errors. If there's a meta lesson across these 4 error slides, it's this. Java's compiler messages are usually telling you the category of problem, naming, types, structure, entry point, or syntax. If you learn to classify the error quickly, your debugging becomes much faster, and that's especially valuable once we start debugging concurrency issues that are not as friendly as missing semicolons. We're starting part 2 with the smallest complete Java program because it exposes Java's shape. In Java, everything lives inside a class. Even if you're writing the simplest script-like program, you still wrap it in public class hello world. Then execution begins at one very specific gateway, public static void main string args. That exact signature is what the JVM looks for when it launches. If you get it wrong, you might still compile, but you won't be able to run. This slide also reinforces the syntax discipline that will make the rest of the course painless. Statements end with semicolons, and curly braces define blocks and scope. That scope concept matters hugely later for concurrency, because we'll be careful about where variables live, where shared state is declared, and what a block of code contains logically. The mental model box is the correct hierarchy to keep in your head. File, class, main statements. If you can mentally trace that chain, you can debug a lot of beginner issues quickly. And the gotchas list is not theoretical, minus case matters, hello world.j versus hello world.j, missing static breaks launching, and missing semicolons causes compilation failures. The goal is we don't want to waste cognitive energy on these once threads enter the story. Now we move to variables, and Java forces a fundamental distinction early. Primitives versus references, int, double, boolean, and char are primitive types, values stored directly. String is a reference type, your variable holds a reference to an object. That distinction will matter later when we talk about sharing data across threads. Primitives are copied by value. Reference variables can point to shared objects, and that's where most concurrency pitfalls live. The first block is classic explicit typing, int x equals 5, double pi equals, and so on. Java's static typing is a feature here, minus it makes intent clear and catches mistakes early. Then you see var type inference introduced in Java 10, var count equals 10, infers an int, and var message equals hello. Infers a string. The important nuance is that Java is still statically typed. Var doesn't make it dynamic like Python. It just tells the compiler infer the type from the right-hand side. Finally, constants. Final int max equals 100. Final means you cannot reassign the variable once initialized. That idea becomes powerful later in concurrent programs. Reducing mutability, making more things final, often makes code safer and easier to reason about. For now, the rule of thumb is solid. Use explicit types while learning, and use var only when it improves readability and the inferred type is obvious. This is your quick map of Java's primitive types, and it's worth knowing the rough boundaries because silent overflow and truncation can create subtle bugs. For integers, byte is 8-bit, short is 16-bit, int is 32-bit, and most common, and long is 64-bit minus, and notice the L suffix for long literas for floating point. Float is 32-bit with an F suffix, double is 64-bit, and is the default for decimal literas. Char is 16-bit Unicode, and Boolean is simply true-false. Then we get to conversions. Java distinguishes widening and narrowing conversions. Widening is safe and automatic. Assigning an int to a long works because a long can represent all int values. Narrowing can lose information. Going from long to int requires an explicit cast int y. That cast is you telling Java, I accept the risk. In concurrency contexts, types matter because shared counters, indices, timestamps, and sizes can overflow or truncate in ways that only appear under load. So even though this is basic syntax, it's setting up a habit. Know what type you're using, know its limits, and be explicit when you cross boundaries. Operators are simple, but Java's behavior has a few gotchas that matter in real systems. Arithmetic operators behave as expected: addition, subtraction, multiplication, but look closely at division. Int quote equals 5 divided by 3 yields 1 because both operands are integers, so Java performs integer division. The remainder operator percent gives 2. That integer division rule is responsible for a lot of why is my average 0 bugs. Increment and decrement also appear x plus plus and plus plus x. In isolation they both add 1, but in expressions they differ in when they produce the value. For beginners, the safest advice is use them as standalone statements until you're comfortable, and avoid clever expressions that combine increment with other logic. On the right are comparisons and Boolean logic, equals not equals, greater than, and the logical operators and or not. One critical note for later: and or are short-circuiting operators, meaning Java may not evaluate the right-hand side if the left-hand side already determines the result. That can be a feature, but in concurrent code it also means you should be careful about side effects inside Boolean expressions. And the gotcha box is the one to remember. If you want a floating point result, force a floating point operand like 5.0. We've covered the first part of our Java programming primer as preparation for using Java in concurrent programming. Please watch the next video, which goes deeper into Java syntax. Divided by 3.